it's coming up. Yes.
Yeah.
Oh, okay, great. Okay, can I start now?
Yes. Can start.
Okay, good. Okay. Well, first, welcome. I mean, good afternoon, and here is good night, everyone. The title of my talk is modeling the quantum vacuum as a dielectric medium based on the Maxwell theory. Okay, so we know our universe is generated from the vacuum. Is the vacuum in the sense of the quantum vacuum, not the mechanical vacuum. The basic postulates in my work is the following. Okay, the universe is filled with a vacuum medium, and all particles are excitation wave of this vacuum medium, and different type of particles are different excitation modes of the vacuum medium. So therefore, both the photon and the electron are excitation wave of the vacuum, but of course they propagate in different excitation modes. So the key question is, what's the physical property of the vacuum? Now we know the vacuum must be isotropic, homogeneous, and massless. You know, a century ago it was thought that this vacuum is almost like even light. But of course, you know, in the end of the 19th century or the beginning of the 20th century, people have some question about it, and the even model had become disfavored. Now, in our case, we are inspired by the even model, but it's not the same as the even model. So what we propose is that the vacuum is a dielectric medium, and this proposal is based on the Maxwell theory. Okay, so now this is really the key part, is that why we think the vacuum is a dielectric medium and what is supporting evidence. Okay, that's really the main part. So in my 15-minute talk, this will be the most important point. Okay, now if one look at the original version of the Maxwell theory, the original Amber's law was written like that. Okay, so the curl of the magnetic field is equal to the external current. But there's a problem with this original Amber's law because it does not satisfy the condition of charge continuity, which is like that. If you take the diversion of both of these, then the diversion of J is automatically 0. It will not be like that. So to fix this problem, so Maxwell proposed to add a displacement current at the right-hand side of the Amber's law. And his argument is that, you know, if the medium is a dielectric medium, so when you have an electric field, and then electric field will drive this displacement charge, and then the time derivative of this displacement charge will just act like current. It's no different than J. It would contribute to the magnetic field. Okay, and so that was the argument. Okay, now so therefore, that what Maxwell did is only valid if the medium is a dielectric medium. Now later, when Maxwell derived the equation of light propagations, he assumed that the J external current is 0, but the D is not 0. So this is a time differential of D is still there for the vacuum. Now, how can that work? That means he must have to make the assumption that the vacuum behaves like a dielectric medium. Otherwise, this time derivative D or the D itself will become 0 if the vacuum is just an empty space. Okay, now this is a very important assumption, and somehow very few people take note of that, and this is actually a surprise to me. Now, once we know the vacuum is not an empty space, it's a medium, it is a dielectric medium, then we can do some comparison with the other well-known wave medium, such as the elastic solid. So we know sound wave is carried by this elastic solid. Now, in this case, how the sound waves propagate is because the volume element of the elastic solid can go up and down when the sound waves comes by. Now, in the case of these dielectric medium, so you can expect that this electric charge can also come up and down during this wave propagation in the vacuum. Okay. Now, the way to describe them, to have a mathematical treatment, is better to use this Helmholtz theorem, or so people call it Helmholtz decomposition. So what it said is a reasonable vector field can be decomposed into two components. So one is a longitudinal component, another one is a transverse component, and the longitudinal component is also called a curl-free component, and the transverse component is also the divergent-free component. It's okay now? Okay. Now, here's the phi. Here is called the scalar potential, and the psi is called the vector potential, okay? Now, these two, the phi and the psi, each can set up a equation of motion. So they describe two separate wave equations. One wave equation for psi and a wave equation for phi. So this is called a longitudinal wave, transverse wave. Now, let's go back to the vacuum situation. So if the vacuum is a dielectric medium, so what's the basic field? Now, we are not, since it is a very short talk, so we're not going into very technical discussion about the basic field. So essentially what it means is, what is a representation of the displacement of the vacuum, of the medium during this wave propagation. Now, we know in the standard version of the electrodynamics, we already know that the magnetic flux is a curl of this vector potential A, which look very much like the Helmholtz decomposition, okay? And also we know in the magnetic flux case, there's no longitudinal component, okay? So one may think, well, maybe we already have that, so therefore the displacement of the vacuum medium can be described by this vector potential A, which is very familiar in the textbook. But we think this cannot be the case. The reason is not for mathematical reason, but for physical reason, because as we said earlier, the vacuum can be modeled as a dielectric medium, not a diamagnetic medium. And also we know there's no evidence for magnetic monopole to exist alone in the vacuum, but you can see many electric monopole. So therefore, the vacuum must be composed of these different electric charge, but not different magnetic charge. So in that case, the physical parameter representing this the movement or the displacement of the vacuum medium must be related to the electric displacement D instead of the magnetic D. Then we can using the Helmholtz decomposition, and so therefore the D can be decomposed into two terms, the longitudinal term and the transverse term, okay? And again, this phi is a scalar potential and C is a vector potential, but since this is represent the electric part, so when we call this C, this is a new physical parameter introduced by me, and I just call it the electric vector potential, okay? Now, since we know that divergence of D is equal to 0, and in the vacuum, there's no free charge, so therefore, we can write down that D equal to the curl of Z. Now, this looks very much like the counterpart in the magnetic flux. Okay. Now, once we do that, and we can go back to the original Maxwell theory, and it can be shown very easily that the electric field is a spatial derivative of the electric vector potential C, and the magnetic field is just a time derivative of the electric vector potential C. And also, just using some manipulation based on the Maxwell theory, one can derive the wave equation of the vacuum, which is like that. Now, these, of course, remind us, since we know the excitation wave equation in the vacuum is something in this form. So you can see that this form just compared directly. So this wave equation could be just the C. Now, these can also give us some insight by comparing the mechanical wave medium and the vacuum wave medium, okay? In the mechanical wave medium, the displacement, of course, is like a local dislocation of the elastic solid. And we can generate the wave because of the two things. One is Newton's law, and another is Hooke's law. In the case of the vacuum, it is not the Newton's law and the Hooke's law. Instead, it is really basically the Ampere's law and the Faraday's law. Okay, and it can be actually show. Here I'm using a red outline over here that the electric vector potential we define here and the well-defined magnetic vector potential, they are causally interacting using this pair of equation, which look really symmetrical. Okay, but based on this relationship, so it's very easy to derive the wave equation for the excitation of the vacuum medium, which is just like that. And by the way, that this excitation only has the transverse component. It does not have the longitudinal component. That is well agreed with, that we know the photon, like the light wave is the transverse wave. Now, once we know the general wave equation of the vacuum, and then we can look for different solutions. Some of the solution may represent different kind of particles. Okay, so we can look for different excitation mode based on this equation. Now, this wave equation, of course, we're now facing the major challenges of how to identify the particle associated with a particular solution of the vacuum wave equation. And another important challenge is that, can we derive the quantum wave equation for some particle which we already know, such as the electron? Can we derive the direct equation, the Schrödinger equation, and so on? Okay. And my answer is that yes, and actually we did go through that process. Here, because this is short talk, I just give you some maybe highlight of that. Okay. First, about the photon. The photon is very easy. Okay. So using this equation, if we look for the so-called plane wave solution, it has a dispersion relation. Omega is the frequency, K is the wave vector. This is exactly the dispersion relation of light. So this suggests that the plane wave solution represents the wave function of the photon. Now, what about other particle, the massive particle, particularly electron? Okay. Now we can look for the other solution. The general solution of this wave equation of the vacuum, including two parts. One is the a longitudinal, it's a traveling component, a traveling wave component, and a transverse component. Okay, here's the K is the direction of propagation of the particle. Now, using the separation variable technique, that this wave equation can be separated into two separate wave equation, which describe the motion of the longitudinal component and their transverse component. And the solution for these two components is given over here. The longitudinal component of this traveling wave is really just very simple, okay? But the transverse component is actually including two parts. One, this is the Bell-Cell function of the first kind, and the n it could be an integer or half integer, like 0, 1/2, 1, 1/2, 2, and so on. Okay. Now, but in addition to that, so there is also a kind of a helicity. Okay, so there is a dependent on the angle. Now, when n equal to integer, so that's so they can be put into 2 pi or 1 pi or quarter pi. But when n equal to 1/2, this repeating would be like 4 pi. Okay. So here just some examples showing that when n equal to 0, then you can see the transverse wave will look like that, and then when you like electron 1/2 will look like that. And of course, this will take another turn. This is not complete. Take another turn, so it will look different. And then n equal 1 will be like that. Okay. Now, the interesting thing about that is that we call these complex solutions, called a vertex-like solution of the vacuum wave equation. And that has a dispersion relation different than for the photon. There is an additional number here, L squared. Now, this actually, we think that dispersion relation suggests that it is representing a particle with rest mass. And how do we know that? And we know that because this dispersion relation gives the energy momentum relation of a massive particle. Okay, now this can be shown very easily because we know that omega is associated with energy and the K is associated with K. And also further, we know the momentum equal to mass times velocity, and velocity equal to group velocity of the wave packet. From that, you can really derive, you can really show that this dispersion relation directly give you the energy momentum relation, and also the areas actually associated with the vast mass. Okay, and the other relations, the well-known relations, can also be derived. In fact, these are suggested the so-called relativistic relations are due to the wave properties of a particle. So now to just to summarize, because my time is up. So in physics now, there are two different views of the particle. The mechanical view is the wave view. Actually, I noticed from the F-chat, many people in this mini conference have some favorable feeling towards the wave view. So maybe we have more common than difference. Okay. Now in the classical world, the particle is regarded as a point mass, and of course, the physical law should be the Newtonian mechanics. In the quantum world, we think there's no such thing as a point mass particle. They are just wave packets, okay? And the correct way to describe the motion is wave mechanics. But now in the so-called standard model, sometimes people mix the two. Sometimes they use this so-called point mass concept to describe the particle, and sometimes they're using wave. And this sometimes may cause a confusion. Okay. And finally, okay, so this, that in our world, why we think the wave can represent a particle is because even though in the quantum level, in the microscopic level, they are wave, but in the macroscopic level, they look like a particle. And that's because there's a one-to-one correspondence. Because the frequency is related to energy, and their wave vector is related to momentum, and their transfer vector is related to vast mass, and the group velocity is related to the speed of the particle, and the dispersion relation is related to the energy momentum relation. Okay, and if people interested, they can look up some of my previous work. And thank you very much.
Thank you very much for this very, very short talk. My apologies for interrupting. Let us the discussion at the end. Okay, so one, maybe two very brief questions, and John can start.
Okay, yeah. Please, any comment, question will be welcome.
If there is any question, please unmute and ask.
Yeah, this is just a comment, Professor Chang. You have a beautiful mathematical, very cogent and coherent presentation. In my last year's paper, ether holds the 100% energy, and this is the platform. I have said the same thing as an experimentalist, and actually derived Maxwell's wave equation using Newton's second law, and there I redefined epsilon naught rather as epsilon naught inverse as a electric tension and mu naught as magnetic resistance to bring analogy with the mechanical string wave propagation. I will send you that paper. It's
yeah, please. I would like to.
I mean, you have a beautiful mathematical presentation. What I have conceptually hand waving way I have published last year.
One comment.
Okay.
Professor Chang, John Williamson here.
Yeah.
Are you familiar with De Broglie's thesis, where he describes the relativistic relationship between a relativistic wave particle and derives De Broglie's P as h bar k from that? In other words, what you're showing as a result was actually a thing which he derived as a in the beginning of De Broglie's famous relation. So you should have a look at it, and there's a lovely translation of that available in English now, and has been recently, just for information.
Do you say Dubai or the? Sorry, I mean.
No, De Broglie, Louis De Broglie.
Oh, De Broglie.
Yes, his thesis.
The French,
read his
the
thesis.
French physicist. Okay, yeah.
Yes,
okay.
yes,
I mean,
that guy.
The famous
De Broglie.
correlation. Okay. Sorry. My hearing is not very good, so that's why.
No, it doesn't matter about the hearing. I'm not worried about that.
Okay. Yeah,
It's just
yeah.
that
If you
Roy
find
did the
that
same thing as you, but the other way around.
I welcome. Yeah, please,
Good.
please. You know, I mean, this is like helping, okay? Because I
Read
like
it.
to know. You know,
Yeah,
because
good.
science is something that you keep working together. Everyone, you know,
Yep.
you build
Yep.
on other people's knowledge. Okay, so
Yeah, that's
I
right.
welcome that very much. Okay,
It's
so
a
I would like
beauty. The
I
French
need
is beautiful.
to
If
know
you read
what
French,
people
it's
think.
fantastic.
Thank you very much. So now John can start.
I have to get my screen shared here.
Okay.
I gotta go to,
Next one.
okay, so I do appreciate the previous talk because it fits perfectly with mine. And so my presentation is a wave-based model of the universe. And it summarizes a soliton electron model and also makes 3 predictions. The quantum field theory predicts that the quantum vacuum has Planck energy density. This is roughly 10 to the 113th joules per cubic meter. However, the observed energy density of the universe is 10 to the minus 9 joules per cubic meter. This model assumes a single field, and I'm going to call it the universal field, is the foundation of everything in the universe. This field has a mathematical energy density of 10 to the 113th joules per cubic meter. This field is not observable because it's missing an excitation. We all know that particles need excitations in their field. And so I'm going to then have this starting assumption. On the scale of Planck length, the universal field has Planck length vacuum oscillations at Planck frequency. This is a quantifiable quantum mechanical acoustic medium. All of the properties of this field equal 1 in Planck units, in natural Planck units. Here I have one way of depicting this. These oscillations are at Planck frequency and they're fluctuations that are Planck length. The structure of the universal field, the oscillations are at the speed of light. If we multiply Planck length times Planck frequency, we get c, so that this is a natural reason why waves in this medium should propagate at the speed of light. The impedance of this medium can be expressed 2 different ways. One is this c cubed over g equals 4 times 10 to the 35th kilograms per second. This, by the way, is derived both from that assumption that I started off with, but also people working with gravitational waves have determined that the gravitational waves seem to be encountering this impedance if you assume that they're propagating in a medium. This impedance is so enormous that a wave rotating at the electron's Compton frequency and wavelength generates an electron's energy with an undetectable amplitude of Planck length. So the universal field is also a superfluid. So now we're going to look at superfluids. Superfluids isolate angular momentum into h-bar quantized rotating units with wave particle properties. Here we have a picture of a Bose-Einstein condensate, which is the most perfect of the superfluids. And when small amounts of angular momentum are introduced, rather than the whole condensate rotating, we find that it breaks into small rotating vortices, each one with h-bar angular momentum. So I'm saying that this is analogous to the electrons in the universal field. They are also quantized rotating solitons in the superfluid field. So I'm going to break this into 2 parts. My model has a rotating wave in the core of it. And here we have just a representation of a Planck length distortion of space. And it is rotating at the electron's Compton angular frequency. And the radius of this core is 3.86 times 10 to the minus 13 meters. This is a representation of electrons' rotating core, and it's surrounded by rotating standing wave cloud. I can't go into all the details of how this model was built up in a short time, but we have a core region and it's disturbing the surrounding universal field. And that this should be dropping off in intensity rather than is uniform, and it really extends on indefinitely. So when I take this model and I start to look at it in a moving frame of reference, it has these moving bands through there, which are the de Broglie wave characteristics of an electron. So this, what I'm saying is one of the design characteristics was getting this de Broglie wave these de Broglie wave properties the way they should be. One of the analysis that I went through looks at traveling waves going both directions with slightly different frequencies, and you then make these moving modulation envelopes, and this is related to the to the de Broglie wave characteristics. This model creates an electron's de Broglie waves and special relativity properties. So one thing is to think of it initially like we have a laser, and in a laser you have waves traveling both directions, so you have standing waves. In the laser, if you look at it in a moving frame of reference, if it was moving to the right here, you then end up with these modulation envelopes formed because of the different apparent Doppler shifts, and it creates a difference in frequency. And you end up with a modulation envelope wavelength that corresponds to the de Broglie wavelength, but also you end up with a relativistic contraction that not only is this the contraction, it also has a relativistic time dilation, a relativistic energy increase, relativistic kinetic energy, and inertia. We get inertia without needing a Higgs field, and then it gets the de Broglie wavelength and phase velocity. All of these are correct. As I'm going to talk now, there is one concept I have to get, which is that I'm going to be talking about waves that are oscillating between plus Planck length and minus Planck length. But so normally you might say that's the amplitude of the wave, but there's another way of specifying a wave amplitude, which is the slope of the wave as it passes through the 0 point. And I'm going to designate with this with a script A, and mathematically in this particular case, it's Planck length divided by the electron's Compton angular wavelength. The electron's Compton angular wavelength, again, is 3.86 times 10 to the minus 13. So when you get that out, this is 4.18 times 10 to the minus 23. So when you see this symbol, you can just say this translates into this specific dimensionless number. For comparison, a muon has an amplitude of roughly 10 to the minus 20. So the calculation of an electron's energy using the electron model, I'm going to start off with a very simple equation that relates to the energy of waves. You have a numeric constant, you have an amplitude term, you have a frequency term, you have the impedance, you have the volume that the wave is, that you're going to calculate the energy for, and then you divide by C. When I take all these various components and put them in here, I get this. And when you then multiply it out, you end up getting the electron's energy, which I want to emphasize. In other words, it's one thing to say, oh, I'm just going to make an assumption that I get the electron's energy. No, if you put it in correct impedance, the correct volume, the correct frequency, amplitude, and so forth, then this model gets that. So in fact, as I was going through this was the first success that I was on the right track. The calculation of the gravitational force between two electrons. So I start off with the universal field has a maximum frequency, which is Planck frequency, and this makes it a nonlinear medium. The standing waves in a universal field create a linear distortion and a much weaker nonlinear distortion. The electron's electric field is the linear part, and the gravitational field is the very weak nonlinear part. Inside the core, the linear first order strain amplitude is this amplitude that I talked before times the square root of alpha. I can't get into the details of how that gets in there, but there is a rationale. The second order nonlinear gravitational strain amplitude is this amplitude squared. It turns out that when you're dealing with waves that are nonlinear, you have a first order that is the linear part, and then the nonlinear expansion starts off with amplitude squared, and that's where I get that. Calculation of electrostatic forces between two electrons. So I'm now going to have a similar equation, except that I have force. And before in the energy equation, I had amplitude, I had volume. Now I'm switching the area. So it's like we have waves striking an area. So previously I worked out with the impedance, the numerical constant, the frequency, Compton angular frequency. So I'm going to now be dealing with two different forces, the electrostatic force between two electrons and the gravitational force between two electrons. The area that I'm going to use in this is the Compton angular wavelength squared times the numerical constant. So now the one point that I have to then make is that when I'm now going to be dealing with forces between two electrons, it turns out that here we have an example of the core and another electron placed in the field that is being disturbed by the first electron. This other one also has its own waves, but I'm ignoring those. So in this example, I have the second electron core 4 complete Compton wavelengths from the first, or 8 pi Compton angular wavelengths from the first. I'm going to be dealing with distance not in the number of meters, but the number of Compton angular wavelengths. I'm defining the number with this script n. And if you take the radial distance divided by the Compton angular wavelength, you get what this distance is in the number of wavelengths. But it turns out that the only thing I have to change for the difference between the electrostatic force and the gravitational force is the strain amplitude. So when I'm going to calculate the strain amplitude for the electromagnetic force, I have this amplitude term, and I'm going to divide it by the number of wavelengths here, and then the square root of alpha. For the gravitational calculation, all I have to do is go to the nonlinear expansion, the first term being this amplitude squared, and again dividing it by the number of wavelengths. So I now get to predictions. An electron's electrostatic and gravitational forces are closely related when expressed using the electron's wave properties. So to begin with, we have the Coulomb law for two electrons. The electrostatic force, two electrons both have charge E. We divide it by this. There seems to be no connection between that and Newton's gravitational law, which has, in this case, has the two electron masses. So I have mass squared. And if we want to make the ratio between these two, then we combine all these things, the gravitational force divided by electrostatic force, this messy thing here, and it turns out to be a dimensionless number, 2.4 times 10 to the minus 43rd. So there's a prediction that there should be an obvious connection when these forces are expressed using the electron's wave properties. So when I go through and, for example, when I convert this equation into using amplitude, the number of wavelengths, and Planck force is c to the 4th over g, multiply that by alpha, it turns out that in fact this is the conversion to my terms of the Coulomb law. Similarly, this is the conversion of the Newton's gravitational law when I convert it using amplitude and so forth. As you look at this, I find this amazing. You look at this, you can see that these two forces, they both are multiplied by Planck force. They both are divided by the number of Compton angular wavelengths. The only difference is that we have alpha times the amplitude squared and alpha to the 4th power here. So just to test this, we're going to then do the ratio of these two forces, force of gravity divided by the force of the electrostatic force. Looking at this, this is this difference here, and in fact, it makes the exact same force ratio as we previously obtained up here. So we've got a success. I have to tell you, I was quite happy when I first came up with all this, and I thought I was on the right track. So then I've come up with several other predictions, One of these is that I'm going to be able to also derive what I'm calling the electron's gravitational radius. It's this, I'm using this symbol R sub G for the electron's gravitational radius. And again, we take the nonlinear version of the amplitude, which is this amplitude squared, and we multiply it by the radius of this model, and we then get the nonlinear term times the radius gives me a radius, and it turns out to be this number here. This is actually half of the electron's Schwarzschild radius. So this is a quantum gravity equation because it generates the gravitational property using only quantum mechanics. This is entirely quantum mechanics on the right side, and really this is general relativity on the left side. Examples of where this usefulness of this gravitational radius. First of all, if you want to have the gravitational slope at a distance r from electron, this is the equation. The gravitational force between two electrons at distance r, this is the equation. You see that rather than having the masses and the gravitational constant, we just use the gravitational radius divided by the physical radius squared times Planck force. And also even the energy of an electron is the Planck force times this gravitational radius. So then prediction 3, when two electrons collide, the repulsive force is initially a charge E force. So this is very what everybody would say. But I'm now saying that this only occurs up to a separation distance of 2 times the Compton angular wavelength. My prediction is that this repulsive force should increase by a factor of 137 to this equation, which C is missing the alpha, which this is 137 times bigger, at a separation distance less than this Compton angular wavelength. This force increase is the same mechanism that produces a strong force in quarks. I haven't gone into the strong force, but the same model generates the strong force, and there's a residual effect that electrons have that then begin to show up when the two electrons are colliding at closer than this distance. So the conclusion is the model approximately achieves an electron's energy, de Broglie wave properties, special relativity properties, electrostatic force magnitude, and gravitational force magnitude. There were 3 predictions. The 2 of the 3 predictions show how the settled physics using the wave-based model of the universe reveals important new and useful concept. The last prediction that I made suggests that new physics, and that can only be proven or disproven by experiments. So I'm finished. Thank you.
Okay,
John, go ahead, Jarek.
One of the 2, oh, sorry. Go ahead.
So there are question, comments, please unmute and
yes, a couple of things. One's a comment, the other's a question. First thing, there is indeed a running coupling constant on the electron. I worked at CERN back in the 80s, and you do see the force between an electron and another particle, another charged particle, increase as you get closer, but it isn't by a factor of 137. It is a factor related to the fine structure constant, but the running coupling constant is a well-known thing in quantum electrodynamics, and it increases very gradually, but nothing like a factor of 137 at distances under lambda c. That's the first thing. And then the question was, I'm intrigued by your calculation where you have a look at the electron energy. And I'm not surprised you get the electron energy out because you're putting ME in terms of lambda bar C into the thing. So if you multiply the constants, you should get it back out again. But you said it was within 99% of it. I'm interested in the other 1%. What's the 1%?
So I'm saying that I'm using what I'm calling the electron's mathematical radius, and I'm ignoring the energy that is in the electric field and the magnetic field external, so that outside that wavelength, it's something like 0.6%.
It's 0.1% approximately. Well, it depends on, so which radius are you using?
I'm using this 3.86 times 10 to the minus 13. This is the Compton angular wavelength.
Yeah, there's a couple of things. One thing, there's a factor of 2 missing in that because the electron goes around, because of the fermion, it goes around twice, not once. So you should half the radius. And the second thing is there are really 2 radii involved. One of them is that, which is lambda c over 4 pi, rather than lambda c over 2 pi, which is what you're using. And the other one is that the maximum radius of the electron, outside of which the thing can't rotate, isn't given by a radius of lambda c over 2 pi, but given by a radius of lambda c over 2, which then changes the thing to rather than 99%, it would be 99.9% you would get, because that's about 0.1%. Just a couple of comments.
So I'm going to say that obviously further research has to be done, but I'm thinking that perhaps that factor of 2 is associated with the fact that those de Broglie waves look like they have
no, the factor of 2 is that a fermion goes around twice before you get back to 720 degrees before you get back to the starting position. That's where the factor of 2 comes from.
That's another discussion, and I get a different answer of how you achieve that. There really is no physical thing rotating. It's a wave going around, and if you try to rotate a wave, you're already going at the speed of light, so you're going to get a phase lag as you try to rotate it. And in fact,
no, the calculations were, if you want to look at them, you and I were both at a conference in 2016. Martin van der Mark presented a paper on the de Broglie stuff and its motions, which is interesting for you too, Donald, by the way, because that also gives the harmony of phases thing which de Broglie talked about. So Martin's paper there, where he talked about the electron as a beat box, as something which kind of breathes and heartbeats, as it were, and that external beat is the de Broglie beat, but that's calculated properly for the lambda c over 4 pi. So that gives the proper calculations, and all the calculations are in there. So if you want to look at that, I think
we should continue with the next talk.
Yeah.
Yes.
Go for it.
Thank you so much. Please, Alexander, if you can share your slides and start. Alexander, can you hear us?
Chang, just a general comment that again, Jarek, I'm glad to see that you are running it, and John Williamson and John Macken. You would recall that I was running Nature of Light Water Photons under SPIE. That was not the right platform to get into further physics. So from 2005, 2015, then it was terminated. But I'm very glad to see, especially these 2 gentlemen, Macken and Williamson, very actively promoting the development of physics. And
it's very good to see you too, Chandra. You take care.
Thank you. Take care. Okay, continue, Jarek, please.
Is there Alexander? Can you hear us? Sure. Could you share your slides?
So sorry, just screen. Okay. So it is seen, screen is seen.
Oh, no.
Yes, coming.
Yes, it works, yes. Start.
So, okay. Unification of quantum theory and gravity is main problem of the modern physics. Extended electron model created by Kerr-Newman black hole solution as a classical solution of the Einstein-Maxwell equations, and we obtained that it is consistent with quantum electron QAD model. Carter mentioned that Kerr-Newman black hole solution with parameters of an electron, mass, charge, and angular momentum has...
Dr. Burinskii, just an interruption brief. Please go into the presentation mode, slide presentation mode. It will be bigger and better visible.
Sorry, one more. My English bad, excuse me.
Okay, go ahead.
Okay, so Carter mentioned it in 1968 that Kerr-Newman black hole solution with parameters of an electron has the magnetic momentum just that of the Dirac electron. Indeed, the parameters electron, the black hole horizons disappear. And Kerr-Newman solution is not black hole really, but represent a naked singular ring with radius equal to Compton, half of the Compton wavelength. Call it the over-rotating Kerr-Newman solution. Over-rotating Kerr-Newman solution is a topologically non-trivial two-sheeted space similar to wormhole or the Einstein-Rosen bridge. Sorry, next. The structure of the Kerr-Newman solution is determined by gravitation from dragging, caused by light-like fields of the Kerr congruence. Kerr congruence is central part of the structure of Kerr solutions. Metric is extremely simple, is presented flat space-time Minkowski part, and non-linear part is proportional this Kerr congruence K nu. A vector field, electromagnetic field, also is proportional this vector K mu. So the Kerr solution is two-sheeted. His face part and back part. So they differ. The difference because for face part, Kerr congruence is tangent to the Kerr ring and going out the Kerr ring. This Kerr ring and Kerr congruence is for ingoing congruence for back parts of the Kerr solution. Ingoing congruence is going in on the Kerr ring, tangentially to Kerr ring. Kerr ring is rotating with velocity of light. It is central part of Kerr solution. In form, metric represents, as I said before, a Kerr singular ring, shown here, Kerr singular ring, and shown here, Kerr singular ring. And the line, the vertex of light-like rays, like drain hole. So there is two sheets of metric, sheet of ingoing and going through this singular ring, they becomes the outgoing congruence, Kerr congruence. So this two-sheeted character is started by considered by Israel in 1917, considered electron as truncated negative sheet of Kerr-Newman solution and replaced the Kerr disk by a surface with consistent matter distribution. The Israel Kerr disk electron was singular and had half of the Compton radius. It is relativistically rotating. Lopez in 1984 suggested electron model as regularized Kerr-Newman solution, truncated the second sheet and regularized the solution using the cutoff on the classical radius, classical radius of classical size. In result, Kerr solution take the form of a disk of Compton radius and classical thickness. Our Kerr solution, this was started about 60 years ago, is considered electron model another. And principal point is that is published only recently, is based on the Israel and Lopez model, but has two important features. First, Wilson lines, Wilson loops, interacting Wilson loops formed by gravitating frame dragging. It gives strong effect which has not previously considered in particle physics. And second, the electron becomes dressed. The Kerr-Newman ring electron is a classical solution of Maxwell equation. This ring is considered as a barren electron. The truncated Israel and Lopez negative sheet we identify last time with positron. So two-sheetedness is considered as two sheets, sheet of electron and sheet of positron, which forms the electron-positron vacuum of dressed electron, according to Kerr. So, in fact, positive sheet, it is sheet of electron, and negative sheet after reflexing and turning into outgoing congruence is sheet of positron. So these two sheets shown here, metric is, as I discussed, is here, and replacing negative sheet with a mirror space, we obtain two-sheeted space with front and back sides associated with two different Kerr congruences. In this case, two different metric appears and two non-boundaries of two boundaries forming Wilson loops, two Wilson loops with two vector potentials which are smeared along the Wilson loops. One Wilson loops here and one Wilson loops here, different orientation. As a result, classical bar electron is formed by massless relativistic string placed on the boundary of the relativistic rotating disk. One turn of the disk corresponds to electron, and second turn corresponds to positron. Quantum dressed electron is associated with superconducting core of the electron, including the mirror sheet on the as the sheet of positron. Hamiltonian of the massless string, string is massless, and this equation lead to appearance of that Hamilton automatically linearized, and Schrödinger equation takes the form with two contribution, plus contribution and minus contribution. In this case, the moment vector is decomposed in the translation part related to moving particle as a whole, and angular momentum related to rotation of the ring string in direction. Mass of the ring string arises from the relativistic rotation. And in fact, by relativistic rotation, Lorentz shrinks the size of the Kerr ring to point. There is in fact, no contradiction between point particles of quantum theory and ring string contradiction because of ring string shrinks to point by relativistic rotation. The Heisenberg and Schrödinger state vectors are contacted by unitary transformation, in which unitary factor corresponds to kinetic energy of rotation of the string. Classical string acquires longitudinal excitations, which are allowed in the case of non-critical string. Very important part is emergence of the Wilson loops. In fact, action of the Wilson loops as usually with, by this replacement using vector potential. As known, vector potential earlier was considered as not having physical effect, but in fact it has effect of Wilson loop, and another side, this effect was described as Aharonov bomb effect, and another side was considered as a very fuzzy effect. In fact, in Wikipedia, we can see that there is almost unknown, unrelated effects, but really it is just the same effects. Boundary of the Kerr disk has two sharp boundaries. Two-sheeted disk has two sharp boundaries where the vector potential is concentrated and smeared by wave dragging, forming Wilson loop. Wilson loops formed by potential, which dragged is given by this formula, and integrating over the loop gives the phase increment, and this phase increment should be integer, and we give quantization of angular momentum and even the series of quantum states, 1, 2, 3, and so on. Because of that, there are solutions which indicate the possible existence of the other leptons. Wilson loops, we consider Wilson loops 1, but this is analogically, there is Wilson loops 2. The mirror potential creates the mirror border, Wilson loop 2, and integration gives opposite sign. So this signs is really mutually compensated. Gravitation contribution from Wilson loop negative is almost equal compensated contribution of positive loop. However, there is a relatively small asymmetry related with this asymmetry because equal to electrostatic components, because associated with electromagnetic mass of the electron, usually described by this expression. This term is included only in the retarded potential and not in the outgoing, but in the retarded potential of outgoing Kerr congruency, but it's not in the ingoing Kerr congruency. And in the result, we see that, but just this letter M in going in Dirac equation and going in the mass equation usually considered for electron. Emergence of the monopoly anti-monopoly pairs. According to Stokes' theorem, the Wilson loops should generate a magnetic flux equal to half of the quantum of the magnetic field. This means that the Dirac monopoly must be born, but a monopoly cannot be born alone, and a second Wilson loop should create an anti-monopoly. Therefore, the two Wilson loops placed on the boundaries of the Kerr disk create a magnetically coupled pair consisting of a monopoly and a magnetically bound anti-monopoly. That is Cooper pair that gives rise to superconducting state in the core of the Kerr disk. Renormalization, like the usual considered quantum electrodynamic, according to quantum electrodynamics, the rest mass should be formed as the sum of the unknown very big expression which is diverging. A diverging expression corresponds to gravity created mass. It should be reduced by the hidden part during the realization process. So it's all. Thank you for attention.
Thank you very much. Are there any questions, comments?
I have a comment. Alex, I love what you're doing. I think it's wonderful work, but I think you're making two big mistakes. And I think your two big mistakes are what you try to tie it to. You're tying it to string at one end, and that's probably quite a big mistake because they're pretty crazy, some of those things. And then you're trying to tie it to gravitation at the other end, when I think you should be talking about a single universal force. Because I think your work stands alone in terms of doing that. I don't think you need to tie it to gravitation or to string theory. I think it should just stand in its own merit. And I think that people are getting it less attention than it would otherwise have because you're doing that. Otherwise, I think it's wonderful. Thank you.
Okay, thank me. Let me answer. First of all, the string which I considered here is absolutely nothing common with usual superstring theory, because first of all, it is classical string, and it is size of the string is Compton size, because it is absolutely another string. It is not string of string theory.
I know. That's why you shouldn't call it string. That's why you shouldn't call it string.
String because really Kerr solution represents a singular ring string.
I understand, but
yes,
when
it is a string. It is string from classical point of view.
Yes, so don't use the word string. Yeah,
because of vortex and
yes, it is line. It is line. It's Nielsen-Olesen superconducting line.
Yes,
this is placed on the border of Kerr-Newman.
String, it's light.
This is like string. Yes.
No, it's not like
it is
string,
described by string.
Okay, but I think, as I say, I think you're making a mistake by using the word string. I don't know what the word string is in Russian. Maybe it's a different word in Russian, but in English it's... Anyway.
Okay.
Sorry, that was my comment. I'll shut up.
Thank you. So maybe could you stop sharing and if Manfried can just share.
I will try to start sharing.
Could you stop sharing? Start sharing. Okay, let me. I can. It's. I have to. Okay. Yes.
Do you see my screen?
Yes.
So I speak about the geometrical model with which I will describe electrodynamic phenomena. We were asked to answer fundamental questions. I give an answer to the first questions.
There are some problems. The connection is very.
Something wrong?
Yes, so there is some problem with connection.
Very bad. You don't hear me?
No, now it's better.
Now it's better. Yes, and this model has a nice picture of spin. Spin has origin of as contribution to angular momentum also. I don't answer the questions about quantum mechanics, strong and weak interactions. So imagine we have only space-time. What can we explain? We can explain non-trivial metric G mu nu, we can explain gravitation. And I have rotating frames in R3. So these rotating frames I describe with the rotational matrix from SO3. SO3 has a twofold covering group, which is SO2. And this agrees with S3. SU2 corresponds to S3, and we have three quantum numbers, which is pi3 of S3, pi3 of S2, and pi2 of S2. They correspond to spin, charge, and photon number. I have also non-topological excitations, which I can relate to dark matter and dark energy, but this is a side remark. So field variables. Field variables are this rotational matrix D of SO3, or simpler, the double covering group S of SO2, and I call these matrices, these elements of SO2, I call Q of X, like quaternion. So the difference between SO3 and SO2 is that every field configuration is doubled. This means field configuration with plus minus are identical. So, sorry. SU2 is isomorphic to S3, and we need to describe a soliton, we need 1/2 of S3. So this Q of X, this quaternion field, rotational field, has a real part and a vectorial imaginary part. You may know that you can write it with cosine alpha and sine alpha, or with Q0 and Q vector and Q0 squared plus Q vector squared is 1. So this is the basic field. Basic field is Q, I forget the sign, which is element of SU2. I calculate derivatives of Q, d mu Q. These are just tangential vectors on S3. If you have here S3, then this is the Q field here, a point. So to every X corresponds a point on S3. So this means a rotational matrix which describes rotation of a Dreibein, of a triad. Then these tangential vectors are just vectors here. So, and I can define with d mu Q, Q dagger, I can define these vectors, gamma mu vector. With two vectors, I can get an area, and this is nothing else than gamma mu cos gamma nu. And this is, I call curvature, because it has exactly the same formula as curvature in gravitation and in QCD. Now I define the Lagrangian. Lagrangian has the structure, Lagrangian L has the structure, Lagrangian density, 1/4 r mu, so similar to 1/4 f mu in electrodynamics. The prefactor is alpha f h bar c over 4 pi, and in addition, I need a potential term. The curvature term compresses solitons and the smoothes solitons, and the lambda term compresses solitons. The potential term is defined as the following. Lambda is Q0 with some even power. I'm using the 6th power, Q0 to the 6 over R0 squared. I have to introduce a scale R0, which is the size of the electron. So electron covers half of S3, so the upper half. And the vacuum is on the equator here. Here's the vacuum. Here, the vacuum. This is at the equator. So I give a penale to Q0 equal 1. So here we have a penale, here we have a penale, and this is potential 0. Because the equator is double degenerate, it's a two-dimensional sphere, S2 equatorial. I have two Goldstone bosons. This means two photons, right-handed and left-handed photons. There's a relation to other models. It's related to the Sine-Gordon model, increasing the dimension from 1 plus 1d to 3 plus 1d, and 1 degree of freedom to the 3 rotational degrees of freedom. This model is related to Dirac monopoles, so it's dual Dirac monopoles, but soft dual Dirac monopoles, because Dirac monopoles have a Dirac string and the singularity and the origin. The Dirac string and the singularity at the origin are removed, and therefore I get soft Dirac monopoles without any singularity. The model is related to this Kerr model, but the usual Kerr model describes short-range interactions, whereas I describe it as model long-range interactions, Coulombic forces. So now we come to the configuration of an electron. An electron I represent here in space. This is in R3, only a plane through the center of the soliton with the imaginary part of the quaternionic field. So this is the imaginary part, and it's simply a vector n, a unit vector n, multiplied with sine alpha. So these vectors here is this vectors n times sine alpha. So this is a Hedgehog solution. With these Hedgehog solutions, you can describe Dirac monopoles if the vectors have unit lengths n, as Wu and Yang have shown. I decrease the length of these vectors here. Outside they are 1, but close to the center they are getting smaller than 1 because of this sine alpha term. And I remove in this way the singularity in the center. And with this hedgehog ansatz, n equal r over r and q0 equal cosine alpha, this is the real part, cosine alpha, the imaginary part has sine alpha. I describe the solitons as hedgehogs. And I can minimize the energy from the Lagrangian. I get the energy density, and I minimize the energy. I solve the Euler-Lagrange equations, and this is the Euler-Lagrange equation for this direct symmetric solution. I told you that I take power 6 of Q0 to the 6, so m equals 3. Q0 to the 2m, I was writing, so. And there's a very simple solution of this nonlinear equation, and this is simply arctangents of ρ. Rho is, by the way, r over r0. So the radius in femtometers or meters divided by this length scale r0, which is the order of the classic electron radius. Sorry. So the energy of the soliton turns out to be alpha f h bar c over r0 times pi over 4. And I compare it with monopoles. The only monopoles which exist in nature are electrons. And therefore I have chosen this prefactor alpha f h bar c over r0. Alpha f h bar c is 1.44 MeV Fermi, MEC squared is 0.5 MeV, and r0 turns out to be 2.21 Fermi compared to the classic electron radius, which is 2.8 Fermi. So now I can calculate from the Lagrangian the energy density, which is 1 over 4 r mu plus this lambda term q0 over 6 over r0 to 4, and with the prefactor of alpha f h bar c over 4 pi. Now I can calculate what is for my solution the q0. The real part of cosine alpha is simply 1 over 1 plus rho squared. I can calculate the energy contributions to this r mu, and v. So the contribution to the curvature term there's a radial contribution. This is the red one here, which goes down with in radius. So this is the radial energy density. It goes down with 1 over r to the 4. And this is the contribution from a tangential contribution from this curvature energy. And this has a maximum at roughly 0. And the potential term looks like the tangential field and has also a maximum here and the same radial distribution. So this is the red curve. The radial field is the electric field, and it corresponds to electric field energy density of a point like electron. But the point like electron would have energy density going to infinity along here. And you see that this infinity is cut away and everything is finite. Going here, energy density r squared. This is simple geometric effect of the radius of a sphere. So I have 4 types of monopoles. I started with this one, vectors outside and northern hemisphere of S3. I can make 2 transformations. One is center transformation, C, and the other one is parity transformation. If I do a parity transformation, I end up here. And I have 2 quantum numbers. I told you, one corresponding to the charge, and the other one corresponding to the topological charge, which is nothing else than spin quantum number. And this is the spin projection. So this is if I call this quantum number charge quantum number Z equal 1. So electron has then minus E0 times C. So this will correspond to the electron, and it's half topological charge. If you cover the whole S3, then I call this topological charge 1, and this is covering half of sphere, and it's topological charge 1/2. So if I make parity transformation, you see vectors are pointing inside. This means that the charge is changed to -1. So instead of electron, we have positron, and the projection of topological charge is changed to -1/2. So it's spin 1/2, but magnetic quantum number minus 1/2. If I do a center transformation from this configuration, I have to reverse from the northern hemisphere to the southern hemisphere. So this is the north pole, this is the south pole, and yeah, and you see that charge is again the same as here. So this is an electron, but this is electron with spin down. So if I do both if I do only C, this is Z times B. If I do only C, only center transformation, I go from northern hemisphere here to southern hemisphere, and I reflect the vectors. So this is electric charge -1 and topological charge 1/2. So once again, if vectors are pointing outside, then this acts as topological as electric charge of an electron. If vectors are going inside, it acts as electric charge. This is also electron pointing outward. This is positron vectors pointing inward, This is also positron. So these 4 solutions correspond to the 4 solutions of a Dirac spinor. I don't have time to discuss. Of course, in order to get Dirac equation, I need to accept rules of quantum mechanics. This means vectors of Hilbert space represent as solitons. I have to accept Born's rule and the canonic commutation relations, and then I can come to Dirac equation. That's what I wrote in a recent paper. I can compare with Maxwell's electrodynamics, and I find several agreements. Lagrange and his Lorentz covariants, the laws of special relativity are respected. Charges have Coulombic fields and fulfill Gauss law. Charges interact via 1/r² electric fields. This can be shown easily analytically. Of course, I don't have time to show it here. We have a local U1 gauge invariance. This corresponds to the basis on S3. To every point on S3, there belongs a local basis. And if I rotate this local basis, this corresponds to a U1 gauge transformation. There are 2 degrees of freedom of Maxwell's excitation of photons. In distinction to Maxwell electrodynamics, I have electric charges which are quantized, like the magnetic charges of Dirac monopoles. Charge is a topological quantum number. I have mirror properties of particles and antiparticles due to the topological construction. Okay? Particles and antiparticles have the same mass and opposite charge. The mass of solitons is completely due to field energy and finite. Charges and their fields are described by the same degrees, same as the 3 degrees of freedom, and these are interpreted as orientations of spatial tribands. Spin has the usual quantization properties and combination rules. There are 4 basic configurations of solitons corresponding to the quantum numbers of Dirac spinors. There are distinctions to Maxwell electrodynamics, but I think my time is over and I have to stop. Rather unexpected is that spin and magnetic moment are dynamical properties. Yes, electric and magnetic fields are perpendicular to each other, as we know from vacuum and Maxwell electrodynamics. Yeah, final sentence. Physics is measurement of distance of objects and times of events. This may indicate that physics is geometry and not algebra. We should use algebra to describe the geometry. In general relativity, Wheeler told space-time tells matter how to move, matter tells space-time how to curve. And in addition to electrodynamics is charges and electromagnetic fields tell space how to rotate. Thank you very much.
Thank you very much. Are there any short questions, comments? Yes.
Manfred, I really enjoyed that. There's one thing I missed, though. I missed the boundary conditions that you had. You stated that boundary conditions on the charge density were R over I0. But what limit did you put on that? Did you put a fixed boundary, or did you? What did you do?
No, by construction, the field is everywhere finite, and the calculation gives finite value.
Yeah,
And
but
I adjust this value.
Yeah.
I adjust this value to the mass of electrons. That's it.
Ah, okay.
There's
So
a
you
scale
put a
there's only one parameter. There's
Okay,
only
so
one parameter. This is R0. This is the size
I understand.
of the soliton.
I
And I
understand.
adjust this size to the electron mass.
Okay, okay, I understand. So you've put essentially a cutoff on the integral energy, that should be mc squared.
No, no cutoff. No cutoff.
You just said that you limited everything to the mass of the electron. That's a cutoff because your hedgehog showed an increase going outwards, getting bigger and bigger.
Adjust. No, you see. Wait a minute. Wait a minute. I have to go back to my.
Yeah. Okay.
I will also talk about it.
Yeah, this thing.
You see, I get an expression for the energy of the soliton, which is finite. The only parameter is this parameter R0, which is a parameter in the Lagrangian. You see this?
Okay,
this
so and that parameter corresponds to the mass of the electron. Okay, I get it. Good. Okay, I missed it.
Yeah.
Thank you.
Okay, thank you very much.
Thank you. So I will start that. I will continue. So it's very similar model.
I will stop sharing. Sorry.
Yes, yes. Okay, so if it's okay, so maybe let me. Okay, so if somebody could.
How do I stop sharing?
You can see my slides, I hope. Okay, so let me start. I think I have sent the slides to the chat. Okay, so let me start. So my approach is a kind of expansion of Manfried Faber approach. Okay. So the main idea here, maybe let me okay, I think it's better now. The main idea, the main problem here is to repair electromagnetism, what Manfried has done. So there are two problems with electromagnetism. One is infinite energy of point charge. So we need to do some regularization. The second is the Gauss law can get any charge being a real number, while in nature it's integer number. So for the charge quantization we interpret curvature of some deeper, let's say, unitary vector field like in Manfried model as electromagnetic field in dual formulation. This way the Gauss law counts topological charge, so we get built-in charge quantization. And for the regularization to finite energy, we don't do stops, but we use this Higgs-like potential. So we have like Higgs potential, so it prefers unitary vectors. So far from particles, we have unitary vectors, but it allows them to deform to, let's say, zero vector in the center to avoid infinite energy. So this is kind of Manfried Faber approach in this electron model. So, but it misses a few things like magnetic dipole moment of electron, like the 3 leptons. So my expansion is kind of from uniaxial to biaxial nematic in language of liquid crystal. That I start recognizing these twists of the field Manfried is using. So I'm starting recognizing these twists, and I interpret it as quantum phase. So now I have a field in vacuum of three vectors, not one but of 3. So one is the long one, and now I recognize the twist. So now I can have a hedgehog as a charge, electric charge, using one first, second, or the third axis. So I get 3 types of hedgehog, and I interpret them as 3 leptons because they have the same topological charge as electric charge, but they have different mass. So we get also if trying to align the second axis on the surface, we cannot do it due to this Kerr-Newman theorem. So we have additional singularity, magnetic dipole like conflict. So we get magnetic dipole moment from this conflict from Kerr-Newman theorem. Also, going to 4 dimension, we should get not 3 by 4, but 4 vectors in every position. So I imagine that there is this 4th vector along time direction, and its tiny perturbations get a second set of Maxwell equations for gravity. I derive it from this very simple. So here is nearly the entire model, the Hamiltonian I'm using, and it has both electromagnetism from the fields of this long axis and low energy Klein-Gordon like equation for the twists, And in space-time, for the axis toward time, I get additionally the second set of Maxwell equations for gravity. It gets from this kind of very simple Hamiltonian. So let me briefly go through. So it's kind of similar to Kerr-Newman approaches, but with difference that they use potential with single minimum, so they have trivial vacuum, while we are using Higgs like potential. Thanks to that, we have non-trivial vacuum with long-range interactions, like for Coulomb interaction. So in Kerr-Newman model, they don't have long-range interactions. So it's very similar to liquid crystals, as I have mentioned, and for liquid crystals, they observe many of these long-range interactions like Coulomb interaction. And here are for basic model for liquid crystals. There is this Austin-Frank model, similar to Manfried Faber model, and this round-up again similar to what I'm doing, additionally recognizing this twist of this molecule for the axial nematic. So this is Lagrange and I'm using. So they are missing, for example, they are missing time derivative, they are missing Lorentz invariant. So this is kind of replacing the kinetic term they are using with something which leads to electromagnetism. So the first property of electromagnetism is the Coulomb interaction. So here is simplified derivation from Manfried Faber. So we take two topological defects in this field of unitary vectors, which should be regularized in the center. So now it's infinite energy, but it has to be regularized. Now it's cut off, but finally this cutoff should be regularized and using the Higgs potential. So we put them in various distances and we calculate the total energy by integrating. So there is integration of energy density, which is visualized with the colors. And doing this integration, numerical integration, you get the Coulomb potential. So effectively, these two topological defects get Coulomb-like interaction with tiny deformation. So Manfried Faber didn't mention, but there is a tiny deformation there, and it corresponds to this running coupling effect, agrees with this running coupling effect as the finite effect of finite size to make energy of electric field of charge finite, 511 keV mass of the electron. Okay, so for electron is more than a charge. So it has also magnetic dipole moment. It's a tiny magnet, for example, leading to ferromagnetism in magnets. Also has angular momentum. And has this clock also. So there is missing. So for this Hedgehog as Manfried Faber model, I'm saying that there is also continuous twist, evolution of this twist of these vectors, low energy, and it is this clock I want to get, but I don't have full proportion for in this moment. But there is this degree of freedom of vacuum for this quantum phase. It is governed like Klein-Gordon-like equation, but not exactly. Okay, so let me talk about further particles. So here are the three leptons by the Hedgehog of one of the three axes. Then I have these fluxon-like, these Ablikosov-like strings. They are called by strings, but they are, let's say, fluxons maybe, if cross-section like this. And so there are three of them. So they are very stable, like kind of neutrino, very stable. Three masses, we can oscillate kind of between them. By rotation, you can go from one to another. So they kind of resemble neutrinos. Then we have more complex knots, like this simple knot that you have one, this fluxon, and the second around it. And it's kind of resemble baryons. So what is very interesting is that this external loop around it changes the configuration of its internal. So it enforces this kind of hedgehog-like configuration, this external loop. But we know that full hedgehog is electric charge. So what we get that baryon structure itself enforces some electric charge. This simple observation, consequence of this model, shows why protons are lighter than neutron, because proton can just enclose this hedgehog, this charge to full charge, while neutron has to compensate it. So we have plus enforced for baryon, but then compensated externally. In deuteron they can share. So here are some better views. So there are at least theoretically I have found that with charge distribution of neutrons. So we assume that they are quarks. The question how these quarks are distributed. And so usually it's shown that there is core positively charged core, and negatively charged shell of the neutron. And it's exactly what was predicted by the model. It gives nice intuition why proton is lighter than the neutron, because proton encloses this hedgehog, neutron has to compensate it. And for the deuteron, two baryons share one charge. So, for example, we know that deuteron experimentally has very large electric quadrupole moment, and so it is very non-trivial for proton plus neutron as deuteron. And here we get it because we have plus, and minus. Also, there are aligned spins. Okay, so we need these strings, these fluxons because of vortex in vacuum here. So there are a few arguments for that. So some are this in sans corona that they observe this one-dimensional structure, and there are suspicions that they are topological nature like this because of vortex. Also the halon neutrons. So we have some like lithium-11, some nuclei which have very stably aligned for milliseconds, or approximately two neutrons in larger distance than of nuclear force. So in very large distance. There are, for example, these many suggestions for quark strings. They call it one-dimensional structure. So there are many suggestions that we have one-dimensional structures, maybe topological, hopefully. Okay, so some calculations. So in 3 dimensions, I get rotations. I get the electromagnetics, and plus adding this gravitational, this 4-dimensional rotation. So we get second rotation, and for here we have electromagnetics, and here we get gravity electromagnetics. This gravitational correspondence. So we get 2 types of spatial rotation: this spatial rotation and this temporal rotation here. And looking at the curvature as in Manfried for space, we get electromagnetics. We get also this temporal. We get second curvature, which gives the gravity electromagnetics. So we get natural unification of both. And we have also the interaction. For example, we see interaction in the bending of the photons going near the sun. So it is kind of interaction between electromagnetics and gravity electromagnetics here. So also we can see that electromagnetic propagation is slowed down in the presence of strong gravitational field. So through the Fermat principle, we get the light bending. Also having slowing down of electromagnetics, we can get time dilation as entire chemistry is based on electromagnetic propagation. Okay, so here we have these leptons, these antileptons. So we get nice unification. For example, if we have this momentum operator, so here is one derivative, and I'm saying that A is also a derivative of this kind of generalized phase, which combines both quantum phase and electromagnetics into one this rotation, SO3 rotation of this object. Also, so let me slowly. So here is a mathematical derivation available in GitHub. That I just put this simpler Lagrangian, calculate the 3 Euler-Lagrange equations for these 3 generators, rotations of this long axis and the twist, and I get kind of automatically the Maxwell equations for the two tilts, and for the twist I get nearly Klein-Gordon-like equation. So here is example of derivation of Klein-Gordon-like equation for the twist. So I get the hedgehog, and I parameterize this twist of this object, and now from this parameterization using the equation, automatically get this formula, which turns out similar to Klein-Gordon for this parameterized twist automatically. So there is some difference. So there is this additional term which is not in Klein-Gordon. Also, there is missing mass in this moment. So in this moment. So this mass is very important because having this mass, I would get also the clock. But now I don't have the proportion for the twist. So now the question is how to get this mass. I hope from the gravity. I'm working now. Okay, so and for the gravity, so here is an analogous derivation of gravity. Now I'm assuming that electric and magnetic field is 0, and I only rotate this temporal direction, and I get a second set of Maxwell equation. Now for this rotation, this temporal rotation. So these gammas, not spatial rotation, but kind of temporal rotations, I get second set of Maxwell equation automatically for gravity. So now I have some problems why how to get Newton attraction. Instead of naively, we have two sources of curvature as masses, and now if you take them together, we add the curvature. So naively, we have increase of energy. So naively, we have repulsion. The question is how to get attraction. So I hope from the signature of space-time, it changes the sign, and I hope also it will also give a repulsion, propel the clock, this twist of this clock. And this is the final slide. So this is nearly the entire model, very simple. So Ermini, so there is curvature of some field inside, defined by this generalization of Manfried Faber curvature with Higgs-like potential. And so this is kind of F mini, but a bit larger, including also phase evolution and gravity. One simple unifying both, so it unifies all. It gives 3 leptons, neutrinos, baryons with protons lighter than neutron, and many other similar objects. So I hope that finally, after looking at effective description of this model, I should get something similar to the standard model. Okay, thank you. So please, somebody, please unmute and make remarks, questions.
I might have missed it, but how big is your electron model?
So in this part, I'm relying on Manfried Faber model. So it should be very similar. And in Manfried Faber model, the size is I don't even two. So here is this is 2,2, I think, femtometers. So it's like the size of electron is a big difficult question. So there are I could discuss, but maybe let's take it to the further. So but generally as in Manfried Faber generally approach.
I have a question too. You put twists starting on what looks like a Mobius strip. Would the same spectrum result if you started from something which was a double loop twist, so a non-Mobius strip as well, or would that change?
I'm just postulating a field, and here I'm just looking what is the space of topological excitation of this field, and I'm trying to find the corresponding particle physics. So for Mobius strip I have used. So for me, so the question is how to get the strangeness of baryons. So yes. For me the baryons are the simplest knots. One is fluxon in the center and loop around. It enforces the electric charge, making proton lighter than the neutron. And for the question how to get the strangeness, and I think that this loop around could have internal twist additional.
I think you're right, Jarek. That's good, and I think that I'll say this when I give a talk eventually when I get around to doing that. But I think what's happening is you start out twisting something, and you end up with something that again looks like a string, or looks like a tube, and then you take that and then you twist it again, and it's that gives you the difference between up and down and strange and charmed, and it gives you the difference between electron, positron, and muon and anti-muon. So I think that's the right kind of approach.
So why I think it's interesting because having this internal twist, it would release this twist, producing this kind of pions. So I interpret it as pions. So this internal tension should release these pions, and we can see it in baryon, strange baryon decay, in count decay. So it agrees.
You're thinking about this kind of thing. I thought about it many years ago, but it'd be good to talk at some stage. Either have you come and visit me, or I'll come and visit you. Okay, good. Thank you.
Let me be on time. So let me stop sharing. And now Samo, I think. Yes. So if you can share your screen and start presenting.
Yeah. Okay. Thank you. So first of all, I would like to thank you very much for organizing this. Let me just see what is wrong. Oh, what? I don't know what.
Everything is fine. So it can be like that. So don't worry about it.
Control F5, I think. Control F5.
Control F5.
Okay, go to slideshow. Slideshow, maybe there is slideshow option.
So sorry.
Don't worry. So it can be like that. It's no problem.
Slideshow.
View.
Click slideshow, yeah.
Yeah.
It's also fine like this. It's fine. You can. It's
Okay,
totally
let's
fine.
just, okay, go. Okay, sorry.
Alright.
So I will talk about some excitation in liquid crystals that might be interesting for you. So I'm not very familiar with these models, but what we observe some excitation that we think that it might be of interest for broader audience. So I will talk about line defects. So in line defects, in liquid crystals, it's very easy to monitor them, to create, observe, stabilize. And so it seems that they they're related to this line singularity, other fields, superconductors, maybe color confinement of quarks. And so I will present some things in liquid crystals that I think that might be interesting for you. So if you look at a liquid crystal, you see you can very easily monitor these things. For example, here is some quench, and so you see you have some lines, so we can easily create different lines. And so if you look this, you see we have some lines, and we can manipulate them by laser tweezers. So we can play with them and see what happens. For example, here we have a lot of different lines, and so we are playing with them with electric field. We are rewiring. So this is experiment, and for example, here is a simulation. So what I would like to say, the nematic liquid crystals are very useful polygon to study these things because we have also support of experiment, and so you can test those things. And so if you look at liquid crystals, you see what is important. You have anisotropic molecules which weakly interact, and because they weakly interact, so they have these local fluctuations very strong, so they have this non-collective excitation pass, so the details are averaged out, and what remains is this rod-like behavior. And so this crucially, this mesoscopic rod-like behavior then dominates the behavior. So we have some kind of molecular field. And so I will talk about thermotropic liquid crystals. So when we go from isotropic to nematic phase by reducing the temperature. So you go from SO3, isotropic is S2 to O2 nematic. So here is mistake, sorry. So this is, you have a symmetry group, and so you have a breaking of symmetry. And so I will show you some topological things that might be interesting and might share also things with other systems. So we have the order parameter space in liquid crystals is in fact a half sphere. And so if you would like to identify this line defect, you make loops around some region. And so you see if this loop, then you see how this loop is translated into this order parameter space. And so it can be shrinked to the point, then you don't have the effect. If you cannot not shrink it, you have the effect. And what is in liquid crystals, you have one kind of aligned effects. And so for this line defects, you can define a winding number. So this is a two-dimensional chart. So you just go around the defect, and so you see how does it rotate the field when you go once around. So you have a winding number for this, you have 1/2, and for this one, you have -1/2. So this is two-dimensional topological chart. But you see, you can have also in liquid crystals a region when you switch from 1/2 to -1/2 in 3 dimensions. So if it's in 2 dimensions, this winding number plays the role of topological charge. And so in 2 dimensions, this 1/2 and -1/2 are topological different. But if you have 3D, then these molecules can go out of plane, and so you can continuously go from -1/2 to 1/2. So let me show you here. So you start from 1/2 locations, and then you just rotate around this axis, and so you gradually get to +1/2. So in 3D, this 1/2, -1/2, and +1/2 are topologically equivalent. You can go from one to another. And so this is also shown here. If you have the order parameter space, so it's a half sphere, because up and down orientations are equivalent. You see, you start from this structure, so you go in order parameter space from this point to that point. And so when you go to this, you go from this point to that point. And so you see when you're going from this configuration to that, by rotating the molecular field, you see you are just pushing this loop from this region to that region. So what I would like to say, so if we have this line defects, you quantify, you determine the local properties by this winding number. But this winding number can change. See, you can go from 1/2 to -1/2 continuously. And so let me just show you some things that how you can get. For example, I've read that if you, for example, this gauge theories, something like that. So let us have a loop. Let's have a loop, and let's have here a looping when you have specific ordering and of these locations, and then let us move this loop around so that we got back to the same point. And what let us see what happens if we have this different kind of dislocations. So if we start, for example, with this 1/2, and so if I make a loop, I go around, and so I don't change anything, so that all the time this structure inside is the same. Then if I look from far distance, I see that I get a Hedgecock-like defect. So if you have such a transformation that I go around the loop, and all the time this cross-section is the same, if I look from the distance, this looks like Hedgecock, and so it has charge 1. And so this is three-dimensional charge, and three-dimensional charge I design in topological in such a way that I make a sphere, for example, a three-dimensional surface around the defect, and I count how many realization of all rotations I have. So you see that in fact this if you have such a radial defect, in fact at a small scale it is a ring. So then I start with -1/2 dislocations, and so if I go around a loop, I make a closed loop, and so I do not change anything, the cross section. And if I do, and if I look from far distance, I see this defect that has no topological charge -1. So this one is +1, this is -1. So they can, this is as defect and as anti-defect. So again, so if you look at this loop is this. So if you look from the distance, it has a monopole like appearance, but if you go closer, you see there is a loop. And so you can stabilize these defects topological. For example, in liquid crystals, if you fix the outside molecular field, then you can stabilize this distortions. Okay, then let us have another case when we go around. So we go again around this loop, but what we do this, what we do now in this case, we gradually we rotate, as previously I have shown that you go from 1/2 -1/2 back 1/2. So that you are changing the winding number when you make a loop. So if you make such a loop, and so if you go from, you look from the distance, far field, it is uniform. So this, if you have such a distortion, dislocations, it is chargeless. So it doesn't have three-dimensional charge. And because it doesn't have three-dimensional charge, it could not be stable. So if you would form it, it would then disappear. But you can stabilize it. For example, if you have, for example, a liquid crystal, and so when you quench the system, a lot of these loops are formed because they are not expensive, because you see far the field uniform, so they don't distort. And so if you have a toroidal topology, then they can pin to tors. Why? Because you see they have a winding number changes from one side to another side. And so if you have some object inside that has Gaussian curvature, then the positive Gaussian curvature attracts one kind to winding number and negative another one. So what I would like to say, so if you have such a chargeless loops, you can stabilize in liquid crystals by topology. And so let me think about what might be this relationship to spin. You see, because this winding number in this liquid crystals, you see, it is you can switch continuously. You can go from 1/2 to -1/2 by continuous transformation. But one quantity which is also important if you have field-like objects is the helicity. So this is some example from vortices on water. And so you see that this helicity is conserved if friction is neglected, and so this vorticity and so this helicity is contains of three different geometrical features, and the sum of them is conserved. So if you look at the helicity, you see helicity has three different geometrical component. One is link, one is right, and one is twist. So if you don't have dissipation, then this sum is conserved. So you can convert these things among them, but they should be conserved. So I think that in this liquid crystal, this could roughly simulate what is spin for particles. And so if you go to liquid crystals, so you can also, in fact, calculate this helicity, but you can calculate it just for defects line defects that have fixed winding number, because, for example, this is the case of 1/2. And when you have this 1/2, you see each cross section has the same symmetry, and so you can model this by a ribbon. And if you model this by a ribbon, then you can calculate this helicity. And so it was shown in liquid crystals that this helicity is indeed conserved. So if you would like to stabilize some of this topological defect, in fact, you need one way is that you put inside some colloids which enforce some rotation under the surface, and so you have a different structure of these topological defects, and so you see that this helicity. So here we don't have a link, but we have just right and twist. So the sum of these quantities is conserved. But if you have these twist dislocations, it's a problem because the symmetry change is long, and so we cannot calculate. Okay, so you see when you have this line defects, so you have additional topological quantities. So I mentioned that if you have line defects, you can assign to them winding number. This is you go around. Then you can assign to them three-dimensional topological charge. Then you have to enclose the whole defect. And then you have some additional quantities which are related to topologies. This helicity, for example. And so you see, you can make different configuration out this line defects. But let us just ask: can we make really a lot of different knots out of this? But you know, it's a problem because if you have these line defects, they can reconfigure. For example, we have imposed here a pair of line dislocations, and then we rotate them. And so you see, if you rotate them, they would like to elongate it, and so, but they reconfigure. They reconfigure, and in such a way, they avoid this, that you would all the time increase the length. And so you see this, this can be also observed in experiments. This is experiment done by my colleague. So we can stabilize also these line defects and rotate them so that we can monitor this also experimentally. And so then we can study this different kind of recombining of these line defects. You see here we have some different, what is interesting, line defects always must be close aligned, but if you have the surfaces in liquid crystals, you can pin them at the surfaces. And so you see here we have 1/2, here we have -1/2. And so if we rotate them, in this case, you get a different kind of this reconfiguration processes that you can then studying them. For example, here we have just reduced the size of the cell. And so you see, you start from this defects, and then they line defects, and they form some like Bujem-like structure. And so here I just show this different scenario that we can study how these lined defects combine. And so here I will then finish my presentation. So I just wanted to show you that in liquid crystals, you have this line dislocations, which can, we study them also experimentally using very simple method, just for example, optic polarizing microscopy. And so you see that this topology is very powerful, and we see that these quantities, how these topological quantities are observed, and so you can test this in liquid crystal. Thank you very much.
Thank you very much. And so it is very similar to my models in many ways. So using biaxial nematic, but why you are focusing on uniaxial nematic, yes, I think. Thank you very much. Any questions, comments?
You spoke about symmetry and symmetry breaking. What about the low temperature phase? Is this the ordered phase or the disordered phase?
So you have symmetry breaking. So if you start from high temperature, you have isotropic ordering. So it is SO3. And then when you reduce the temperature, so if you don't have dislocation, you have some ferromagnetic-like order, but you see the up and down equivalent. So you have O2 symmetry. You have O2 symmetry in this case. And so we are interested in this excitation in such a for such a symmetry breaking.
Okay, thank you. So the next speaker is starting. Yes. So
Yes.
Let us begin the discussion. Okay.
Hi. Yeah, I'd like to show you some quantum spin visualizations. So first, I'll show you the standard cup trick, belt trick, and then I'll move on to a program I wrote to visualize spin 1/2, in particular in elastic solids, because this has come up multiple times to see, is it actually possible to have spin 1/2 in an elastic solid? What would it look like? Then I'll briefly talk about how to actually program this if anyone wants to know. And I use quaternions. You might wonder why. And if there's time, I'll talk about charge, but probably I won't get to it. And I think Robert Close will probably talk more about this. So it's basically, imagine you trying to rotate a cup, and they have strings attached here to make it harder. You want to rotate it continuously by holding it in your hand. You want to make it so you don't break your arm. You don't want to spill any content. And also, you want it to be such a way that it has to rotate twice to get back to its starting location. So how do you do that? And I first do it with the strings attached and then with 2 hands, and I pre-recorded it because it's kind of hard to fit it on camera. I'm not sure if you can hear the video, but yeah. Can you hear the system sound too or not? No, okay. So now there's 1 rotation so far, but it's still not the same configuration as we started with, right? Obviously. So we have to go around a second time to get back to the starting position. And you can see the strings are not entangled in any way. You can do this continuously. Then with 2 hands, it's a little harder, especially to fit it on camera. But you can basically connect this cup to the whole universe, basically, and it will still work. Now, of course, we can do this also with a computer program. Now, in this case, I've replaced the cup with a sphere, and this is just a visual aid, okay? This is not indicating any particle or anything. It's just basically indicating where the center is. Now, let's take a look at this real quick, and you can see again, it takes 2 rotations of the sphere to get back to the starting configuration. In addition, what I've done, I've highlighted a few elements in this elastic solid. It's not yet the elastic, I'll show it after, but imagine this was some kind of medium. We can trace elements in here, and you can see they form circular movements. And when you watch it from the center downwards, it goes in the other direction. So this would be the direction. If this red arrow indicates the rotational axis, this would be facing downward. So on the next slide, now let's dig into this a little bit more. So I'm starting here with a flat configuration, and there are actually 2 orthogonal axes of rotation. One of them is the vertical axis, the face, and the other one is actually coming out of the screen. Let me just start the video. So, and if you want to try the software, you can have it for free. You can play with this. So here we have the one axis, which is sort of like a winding of space, and you can imagine you have invisible spheres that you rotate most in the center and a little less outside. So there's decrease over distance. Here is just a cosine function, but of course, obviously, we'll have a different function when we talk about actual particles or waves. And the second one is the phase. So here you can see what happens. Again, you have to the sphere has to go around twice to get back to the starting location. And you can see you can change the different kinds of windings. You get the standard spin 1/2 when you put the winding to 180 degrees. So basically, when you flip the space around once 180 degrees, this is when you get sort of the standard belt trick cup trick movement. But when you use a smaller winding, you can imagine you zoom out, you kind of see it from further away. So, the movement is less extreme. Here, I'm just slowly increasing in the winding. So we are now back to this initial visualization. Now you can clearly see there's angular momentum. Okay, so any element you see here moves around in a circular way, but there's actually no rotation. So, if this is done in okay, I have to stop real quick here. So here I've replaced the belt with, imagine this is now in an elastic solid, like Jello pudding, whatever you like. And I'm just showing 2 planes here, horizontal, vertical, a grid, because it's kind of hard to see, full 3D view. I'm doing the same thing again. So again, I'm increasing the winding here and more, as you can see. And once again, we are at 180 degrees. We are at this place where we have the typical belt trick visualization. And so this, movement does not break the Jello pudding or the elastic solid, whatever you want to call it. It's actually a fundamental, this kind of spinner is a fundamental movement in 3D space. And so I'm doing still exactly the same function, just showing it with a little more or less winding and, playing with the phase. And okay, now you can see, you can also see that it's actually a circular it's a transverse wave, an azimuthal wave that goes around in a circle. So in all the models, all the elastic solid models, this is perfectly compatible. So basically, because my question was, how can we have spin 1/2 explained in an elastic solid model? It has to work in some way. And again, the sphere is only a visual aid. So there's no sphere. This is just so we can see the center. That's all. There's no actual sphere, obviously. And this has actually been inspired by Dr. Mark Snowswell. He has really nice SpinLab program, but it's older and it doesn't work anymore on Windows. So that's why I had the idea to basically write my own software to do this. Now, let's dig even further into this. I think this, okay. So now what I've done here again, it's the same function. It's still the same belt trick, but now I have basically more. Imagine we're visualizing certain points in the elastic solid. Could be Jello pudding. It's probably easiest to image the big pudding. You can see what it looks like. It's almost like a hula hoop movement. Again, it's a transverse azimuthal wave. It's a pure wave. So there's no, in this model, right, there would be no particles. There's just a wave model and that's it. And this is basically the view you would see from far away. So when you zoom in, of course, you get this all twisted space, but now we're looking at this from far away. And so this is compatible, at least, with all the models that are purely wave-based. Several of you, maybe, sorry if I missed the name. And yeah, so that's basically what I wanted to find out. And so that's why I wrote these visualizations. So now let's take a closer look at what happens to these individual, elements in the pudding or in the elastic solid. So what I've done here, I've added a bunch of boxes to see what are these, how is the displacement look like in this elastic solid? What kind of movement would we see? And you can see that this each point here, oh, I'm zooming in here now. So is actually making circular movements. So, and it's not a rotation because it doesn't break space. It's more like a precession movement, like a wobbling motion. It's not a rotation. So you get actually angular momentum without the rotation. And the movement decreases over distance, obviously. So now when we draw the rotational axis, and again, it's not actually rotation. It's more like a precession movement. It's like a wobbling motion, but still, like at every point, you could draw an arrow. At every point here in this elastic solid, you could draw an arrow that indicates the rotation. And when you do this, you can see that you get a dipole. And again, these are oscillations and not actually rotations. And this is again for the Dirac belt version. There are other solutions. And just again, to be clear, there's the sphere is just for visual aid. That's it. Now, interesting, of course, at least to me, the next question is, how would this explain magnetism? Because, I mean, spin 1/2 is the source of magnetism. So how would that work in an elastic solid? Mechanically, I was just curious. So what I did is basically I have now flipped the spin axis around. So we have here basically south facing north. And I've drawn the rotational, it's not rotation, but basically axis at several places. And you can see in this first situation, all the circles, all the points in the elastic solid, they move, the displacement, it moves in the same direction. So the rotational axis, they're all the same. And if you imagine if you have sort of the stress in this elastic solid, right? And you have two choices, you can either move further away or closer. You would always want to have a solution that minimizes the stress, because now when you look at this, the other way, when we flip, so I flipped this around, now we have south facing south, and you can clearly see this results in a repulsion, because now one side is moving clockwise, the other counterclockwise. That doesn't work. So if you calculate, and I've indicated the stress a little bit here, if you had a choice, right, the system always tries to reduce the stress. This would result in repulsion. So at least to me, this seems kind of a mechanical explanation of why the world would spin 1/2 result in magnetism if the universe is some kind of elastic solid. So a little bit, how do you actually calculate this? And it turns out it's really simple. It took me a while, but so what it turns out is that, as you already all know probably, is that SU2 maps to SO3. So this means the typical quantum spin vector, which is often represented with U with the spins, which are both complex numbers. This is actually isomorphic to the quaternions. So we can map this to a quaternion. Now the question, of course, is why in the world would you use a quaternion? And also here, note that when you do this, actually these are the Pauli matrices, which I find interesting. So why would you do this? And that's because in computer graphics and robotics, quaternions are very common, and I write a lot of software, so to me this was kind of quaternions to me are rather simple, because basically they represent the rotation axis and an angle. And here, so the I, J, K are actually rotations around X, Y, and Z. So for instance, the I is a 90-degree rotation around the X-axis, and J around the Y-axis, and so on. And they actually correspond to, each one of those corresponds to a Pauli matrix, which is, very nice, because you can actually directly map the spin to, in this case now, to a 3D model, right? And I have a bunch of links also in the end, in case anyone wants to more details. Yeah, so of course, and now, once you do that, once you see that I and J and so on are just rotations, these rules are obvious, because, when you first rotate around at the X-axis, right, and then around the Y-axis, well, of course, you get minus, you could get -1. So all this is actually, it's actually, I think it should be -k. Yeah, so these rules are actually kind of obvious when you look at it that way. Now, of course, you can use matrices as well, right? So you can actually map any quaternion to a rotation matrix. So if you prefer rotation matrices, it's totally fine. To me, quaternions are easier, because that's just so much easier than have this whole thing here. So how do you actually calculate this? Obviously, we want to have a continuous function, a function of time and space. Now, the time is actually the phase. And in most of the simulations I've done, I have used the vertical axis, so the z-axis here, as the phase. And you can represent this as a function that returns a quaternion. And this is what if you want the matrix version of this is what it will look like. So this is Q of t, a function of time. And then you have the inverse here. You can check that these multiplied gives the identity. The other one is a function of distance. So this is the winding I mentioned. So Mark Snozwell has a really nice document on this. He calls it the winding of space, or the kernel function. That's the part that the winding, and this is the function of distance. So, it might be something like 1/r². Here is just the cosine for simplicity. This is what it will look like if you use cosine and sine. So, at the outside, there's less winding, and you increase the winding as you go in. And so the overall function to calculate this is basically just Q times the kernel times inverse. That's all. I mean, that's really, really simple. You can calculate the whole animation. Now, of course, so actually, if there's ever time, another time, maybe I can also give a longer presentation, because there are many different kinds of oscillators. This is just the simplest solution here, the circular one. That's the easiest one. So you have Q and the kernel function in the inverse. That's the simplest one, of course, but you can actually create many more complex functions. You can even nest them, and they're all valid. They're all valid. None of them break space in any way. There are also other solutions, and this is not exactly correct. I didn't have time to actually write the simulation for this one. You can also have a helical structure. So you can, again, the z-axis is so the phase axis would be the vertical axis here again. And imagine you're holding a rudder in a pudding, and you're making this motion here. So you're not breaking the pudding, you're just making this motion. And now you also stir a big soup. So you're also going around, and when you combine this, you get this helical motion. And again, it's not rotation. It doesn't break space. It's a helical movement, like a wobbling movement. And this would also be a valid solution. And I think maybe Robert will talk about this, but sure. So I think I actually have some slides on charge, but I'll skip that for now, because I'm running out of time. Because also maybe another time then we can talk about this. So in summary, basically, this spin visualized in an elastic solid, it would represent angular momentum, intrinsic angular momentum, without actually rotation. It doesn't break space. It's basically a transverse azimuthal wave. It's compatible with all the models that are purely wave-based and have some medium, whether it's an elastic solid or you want to call it quantum foam or tension field. It would be compatible with such a model. And the spin 1/2, it creates a dipole, so which would explain why you actually get magnetism, because you have these little circular movements. yeah, and maybe, you know, Zitterbewegung is also a big topic. This would be basically mean we have these oscillations going on all the time, which could indicate Zitterbewegung. Are there any questions?
Are there any questions? If you have questions, please unmute and ask.
Or we can also have a discussion afterwards, right? We have like several hour block for discussions.
Yes, yes,
Chandra, that's the most beautiful 3D demonstration I've so far seen in my life.
Thank you. Well, they're actually better one. This is just, it's interactive, so you can play around with everything. So
That's beautiful, beautiful. Thank you.
thank you.
Chantal, could I ask, you're making these things available, but what have you written them in? Is it
Well, there's something called Unity. It's actually a gaming engine to write computer games. And I use C#. And the nice thing is, you know, Unity, the game engine, has quaternions are built in. So it's like, duh, of course you use quaternions. You know, that's like the obvious thing to do. You know,
have you used left-handed or right-handed quaternions, or do you know?
I don't remember. No, I don't know. Yeah.
Well, ij equals k is left-handed.
Oh, sorry. Yeah, that was a mistake. That was a typo. That was a typo.
No, ij is k. That's right. It should be plus k, and jk is I, and you're right on the slide, I think. Anyway,
oh, okay. Well, during the talk, I can't think straight, so yeah. yeah. And plus, the thing is, you can actually, the camera, you can move it around, so you can actually see it from all angles, you know, kind of helps to explain. Like, I wanted to really see them in my head, so I moved around the camera and watched it from all sides, so. Anyway. I think Robert Close is next. So I'm going to stop the share.
Here. So you can share your slides.
How's that? Okay, so I'm going to talk about the elastic solid model of an ether. Can everyone see that okay? All right. So one reason that I think this is an interesting model is because it figures so prominently in the history of physics, and just give some examples here. And also a little history of quantum mechanics. We have Louis de Broglie, first proposed the wave nature of matter. Klein-Gordon came up with a second order equation. And then Paul Dirac came up with the first order equation, which of course became QED and then the standard model. So my contribution to this, not that I'm with these other guys, but is I came up with the classical physics definition of spin angular momentum density. It's the field whose curl is twice the incompressible momentum density. And I also was able to derive the first order Dirac equation from an ordinary vector wave equation for spin density. And an important thing to keep in mind is that the Dirac equation is a deterministic equation that describes the evolution of spin angular momentum density. So the question that raises is whether the standard model can be thought of as simply a decomposition of spin density waves into so-called particles. Okay, so that's what I'm going to be talking about. So the basic idea is if you do a Helmholtz decomposition, which other people have mentioned, the incompressible part of the momentum density is 1/2 the curl of a vector field that I call the spin density. And using that definition, if you integrate R cross P, that's the same as the integral of S, as long as there's no contributions at infinity. And also if you calculate the kinetic energy, that's 1/2 the integral of the angular velocity times the spin density. which means that if you put that in a Lagrangian, the spin density is the momentum that's conjugate to the angular velocity. Okay, so spin density is really a very fundamental variable that unfortunately is overlooked in elementary physics classes. Okay, so just sort of by analogy with the equation for momentum density, where you have a time derivative, convection, and a force. I propose an equation for spin density, which is a time derivative is due to convection and rotation and torque. Okay, so if the only changes are due to convection and rotation, then you don't need any torque. All right, so defining spin density as a time derivative of a vector field I call Q, I come up with this nonlinear wave equation. So the torque is given by the Laplacian. And this corresponds to a Dirac equation using appropriate definition of spin density. Corresponds to a nonlinear Dirac equation where you've got these extra nonlinear terms. And this is the ordinary Dirac convection term. And if you multiply by psi dagger or I psi dagger over 2, then this term in particular becomes the kinetic energy because this is W dot S, which I mentioned before. And if you look at the classical wave equation and take the wave velocity times the wave momentum, which is more or less what you have here, wave velocity times wave momentum, that corresponds to potential energy. And so the time derivative in that, and also for transverse waves, I expect this term to be 0. So that would imply the time derivative would give you the total energy. So there's this nice correspondence between terms here. So if we take the Dirac equation for spin density, which you would get from the electron equation, just multiply psi dagger sigma over 2 and then add the complex conjugate, you would get this expression. This is what you would end up with, this sort of complicated expression here. But I was able to actually derive this equation from the wave equation. And the corresponding terms are the time derivative corresponds to the second derivative of Q. This term corresponds to the gradient of a divergence. And this term corresponds to the double curl. So these two terms combined give you the Laplacian. Okay, and I just want to point out that if you take a one-dimensional wave equation and look at the solutions, the solution is a sum of a forward propagating wave and a backward propagating wave along the axis. And these two solutions are independent states that are 180 degrees apart. So they're characteristic of a spin 1/2 geometry. Okay, so if we look at solutions or consider what solutions would look like, I would say that the odd and even spherical harmonics would correspond to fermions and bosons, because the Dirac representation will always have half of the angular dependence of the vector representation. And the odd spherical harmonics also have odd parity. So those would have distinct antiparticles, whereas the even spherical harmonics would have even parity. So those would not have distinct antiparticles. So that's in agreement with the standard model, except for the W particles, which perhaps are not elementary particles. And then finally, if you calculate the total momentum and angular momentum, you get two components for each. You have the dynamical or wave components, familiar from quantum mechanics, And you also have the intrinsic momentum and angular momentum, which are the usual momentum and angular momentum that you would associate with the moving particle or moving piece of a solid. This intrinsic momentum actually has been derived previously under different circumstances in order to get consistency with general relativity. And in terms of the angular momentum, we have the orbital and the spin angular momentum. And I would argue that the measurement of spin angular momentum is a strong confirmation of this elastic solid model. Interesting thing, if you look at the angular eigenfunctions in Dirac theory and look at how they change due to the mass. So here's angular velocity operator. Here's the mass operator. If you plug in these angular solutions, what you find is that the change of velocity is only in the radial direction. So you have a radial acceleration of velocity as if it's propagating in a circle. Okay, so assuming that you can come up with solutions, which is more what other people have been talking about today, assuming you come up with solutions, you want to treat them as independent particles. So if you add the wave functions together and then calculate the spin density, you get the individual spin densities plus you get these interference terms. So if you want to treat these as independent particles, you have to cancel out the interference. The interference has to be 0. And if these are spin eigenfunctions, or actually just one of them is a spin eigenfunction, that results in the exclusion principle. Basically these have to anti-commute. And then this would not be true if you just plug in a wave function, but you can force this to be true if you put in some phase shifts to cancel out the interference. So the key here is that by assuming independent particles, you can maintain that even when they're interacting if you put in phase shifts so that there's no interference between them. And those phase shifts give rise to the interaction potentials. So just working that out, if you look at the effect of these potentials on the momentum operator, you add in a gradient. And if you look at the effect on the Hamiltonian, you actually get 2 terms. One is a time derivative and one is also a gradient term. And the time derivative corresponds to the electrostatic potential, and the gradient term corresponds to the vector potential. Okay, so these are the definitions of the electromagnetic potentials. And if we work out the rate of change of momentum, we end up with actually these commuting derivatives, 2 sets of commuting derivatives. But because this is a phase angle, these derivatives do not commute, okay, because you can go around the circle and the phase can change by 2 pi, for example. So using this definitions of the potentials and assuming the charge density is proportional to psi squared, and then the current proportional to the wave velocity, we can work out the electric field and the magnetic field here. And so you get the Lorentz force. Okay, so just to give some examples, if you have a pure phase shift, which you might have in let's say a macroscopic system, where you've got everything synchronized into a pure phase, everything's in phase, then if you work out the magnetic vector potential and take the integral, that has to, come back within a factor of pi or some multiple of pi. And that gives you the quantization of magnetic flux, because by Stokes' law, this is the same as the integral of magnetic field over the area. So you get magnetic flux quantization from that. And if you have a phase shift with a weighting, radial weighting, like you might have for a single particle, then you've got the phase shift here, but then you've got this 1/r weighting, and I threw in some factors here. And I just stuck this extra term on the end here. The average value of the sine is 0.6366. This is a way that you might, if this is the wave function, has this kind of dependence, then you break the singularity at the origin. So, but anyway, I'm just going to ignore that factor for now. The vector potential looks like this, and all the flux comes from the phi component. So the magnetic field would have this dependence, which is the same as you would get for the electron. If you integrate to find the flux, it's the same as what you'd get from an electron dipole moment. And if you look at the electric field, assuming that the time derivative is just due to convection of the phase, if you work that out, it ends up being the same as the phase velocity across the magnetic field, and you get the 1/r² dependence. Okay, just quickly, if you try to make a Lagrangian from that for two different particles, A and B, if you apply the Dirac equation to the second particle, you just get tautology here. But then if you transform the interaction fields using some vector identities, you could write that as E² minus B². And in QED, you vary the potentials, but you don't vary the currents, whereas here you vary the electric field twice, basically. So there's a factor of half gets tossed in, but this results in the QED Lagrangian for a single particle. Okay, of course you'd have to generalize to multiple particles to really get QED. Okay, just one last thing. Gravity. If you have a varying density, which as you distort the solid, it's going to cause a slight compression, and also allow changes in the shear modulus. If you describe a particle as being a radially dependent wave function like this, then that's a stationary particle. Then a moving particle would have a Lorentz boost applied to it. So it would look like this with a variable speed of light. The radial dependence varies with the density to the 1/3 power. And the shear modulus varies like inverse of the density. You can think of it like if you take a spring, if the windings are tighter, then the spring is weaker. So that's why this is the inverse of that. So the index of refraction goes like density to the 2/3 power. This is entirely equivalent to general relativity, with the temporal metric components going like 1/(n), and the spatial metric components go like (-)(n). There's an interesting paper by Evans explaining why that's equivalent to general relativity. Okay, so just in summary, these are some of the properties I can get from a solid ether model. And that's finishes my talk.
Thank you very much.
Chandra, okay, go ahead, please.
So-
Jarek.
So please unmute and
The Chandra, Robert, I'm very impressed. Again, it's a beautiful, comprehensive theoretical work. Of course, the whole group is presenting very excellent theoretical work, but yours appeared to me quite comprehensive. And I'll have to spend more time to read your papers. Thank you.
Okay, here's a list of what's published.
Okay.
okay, so